Hello and welcome back to the course on software engineering. Today we're going to be talking about a subject that has been receiving increasing attention of late, and that is of software reuse. If you take a look at traditional engineering methodologies for building other kinds of systems, so for example hardware for building civil engineering, construction, mechanical, etc., you will find that a lot of work that is going to be done to build a new system, component, artifact, entity, whatever, borrows a lot of the ideas, the design ideas, borrows a lot of even pre-built components from other from previously done work. But in software, because it's a relatively new field, that practice of reusing software, what goes into making the software and the software itself is not very well established, and we'll try to take a look at some of the notions in the field of software reuse. What is reuse, what are the problems to reuse, what are the advantages of reuse, what are the different ways of what can be reused, and what are the different ways of doing it is the main objective of this lecture. So design with reuse is a phrase that is often used, and there are actually two phrases that are complementary phrases to one another: design with reuse and design for reuse. Design with reuse essentially focuses on building software from reusable components. So instead of trying to write software from scratch, what I will do is take components that have code built into them, that embed certain algorithms within them, that I know that I also want in this new project that I am trying to put together, and I will simply reuse those components. On the other hand, design for reuse is essentially the reverse mechanism. So when I am designing a component that I am going to use in my project, I consciously make an effort to design it in a more generic, in a more abstract manner, so that it can be reused across multiple projects. So in one view, the software project that is currently being undertaken is a sink for components, and is a sink as far as the reuse process is concerned. The other case, it is a source as far as the reuse process is concerned. So what we'd like to look at today essentially are what are the benefits of reusing components. Although it kind of seems obvious, it is worthwhile discussing what exactly are we going to get out of this, because it has not been adopted very widely. If you take a look at software projects in the 70s and the 80s, it's only in the mid to late 90s has this notion of reuse really picked up, and efforts are being made to design with reuse. So we'll also take a look at some of the different reusable levels, the levels of reuse that can occur. So for example, you can go all the way from the notion of reusing a requirement specification that has already been written, or all the way through to reusing entire systems that have been built. So reusing what are called as common off-the-shelf systems or COT systems, and the entire system can be reused in another instance, right? And we'll also look at the intervening levels of reuse. So application frameworks, for example, is a way of reusing architecture, reusing design, and reusing some code, although some additional code would have to be written in this particular case. And design patterns are a way of reusing designs only. There is no code that typically comes with that, no classes, no abstract classes or anything of that sort. And there then can be component-based reuse or functional reuse, where an algorithm, a certain amount of code that has been written for a specific function can be reused. Example of these could be math libraries, graphical user interface libraries, and so on. And we'll take a look at the different levels of reuse as we go through this lecture. So like I said earlier, in most disciplines, in most engineering disciplines, reuse is a way of life. If you take a look at a typical design for a bridge, you don't design the entire thing from scratch. You basically understand the trusses that make up the bridge. There are kind of pre-built designs for all of these things. So if you know the type of bridge that you're going to build, you're going to borrow designs from existing bridges which have already been done. And they are parameterized. So for example, if this bridge is to be 1 kilometer long instead of the previous bridge that was built, which is going to be 2 kilometers long, you can appropriately scale things down. They have already been parameterized, and therefore arriving at a design for the new bridge is not going to take as long, because you're simply reusing bits and pieces of the design of the older bridge. Indeed, this can extend to things beyond design. Entire parts of bridges may be prefabricated and kept, and you're just using prefabricated components. More and more of that is seen when you're building mechanical devices. When you're building robots, for example, even when building computer hardware, chips are pre-manufactured, and whenever a computer is to be put together, you don't start by making your own chip. You buy a chip that is available that embeds certain capabilities. The CPU is a chip that embeds a processing capability. There are memory chips available of various kinds. So depending on your needs, you pick the set of appropriate components. So for example, if you need a 40 gig hard drive versus a 80 gig hard drive, you pick the appropriate component and you assemble everything together. So you unify all of these, and you may have to do some gluing work, right? In this case, you might have to make your own motherboard, which allows all these components to interact with each other appropriately using the standards that have been specified. But if you take a look at software engineering, traditionally it's been more focused on building all the code all the way from scratch every time, unless it's in the same company, right? So for example, if I were going to build a graphical user interface for an e-commerce website, there have been hundreds of e-commerce websites that have been built. A lot of these user interface notions are already available as pre-built components, but typically the tendency is to build the entire e-commerce website from scratch. You take a HTML editor and sit down and start building the e-commerce website. And over the last 5 to 10 years, however, the realization has definitely come in that this is an expensive process, the first thing, and it is prone to errors. Every time you end up writing new code, you are likely to introduce errors. And so the way of reducing the error rate or increasing the robustness of the software that you're going to produce at the end of a project would be to try and reuse proven code, try and reuse proven components that have been written earlier, that have been tested thoroughly, and have been used in previous production situations. So if you're just able to pick that off and reuse it as it is, then you not only save time, but you also provide error-free code, and we'll look at some of the advantages of reuse as we go along. So reuse-based software engineering can be done at different levels, like I talked about. It can be at the functional level, that is, a single function can be reused. So for example, in a mathematical library, they may provide functions for calculating the factorial of a number, for calculating square roots of numbers, and so on and so forth at the simplest level. And all of these functions can be when you're writing a program that requires calculating the factorial, you wouldn't write your own code. You would simply call this function of a library, and this is a common form of reuse. This has been done from quite a while, but a higher level of abstraction for reuse may be that of a component. So the component embeds a certain set of related functionality into it, and a good example of a component may be a text frame within a graphical user interface. That's a good example of a component. Or it can be something much higher level. A component may embed a more serious algorithm, such as optimizing a certain function, optimizing a set of related functions, and therefore you can reuse the entire component because you may need more than one interface of that component within your program. And yet a higher level of reuse, like we've seen before, is the entire application can be reused. It's called COTS reuse, or common off-the-shelf applications are taken as a whole and basically reused by adopting it to meet the business process and the needs of your particular project. In practice, basically common off-the-shelf reuse is becoming quite common. The functional reuse paradigm has existed from quite a long time. So we have seen libraries that were written in C, that we've seen libraries that were written for Fortran. There are common libraries available for engineering design problems that you can pick up and use that have been available from the last 2 to 3 decades. But component-based reuse, creating components as well as creating systems out of components, is a relatively new science. It is only becoming solid now, and it's only in the past 5 years that component-based software engineering, as it has come to be known, has become a science in its own right. And people have developed ways of describing components which are quite abstract, of gluing together components in a visual manner, and so on, that make software engineering much simpler and much more reliable, more importantly. just to summarize the different benefits that we can get of reusing at various levels, it does not have to be at any one level. The first one is obviously that of increased reliability, that the component, the function, the system, whatever it is that you are reusing has not only been thoroughly tested, because that has been the specialization of the person that has written that component, but it has also been used in other situations before, in production situations, and it has stood the test of actual systems. So that increased reliability that is gotten out of reusing components is something that is hard to beat. Also, there is a reduced process risk, and this kind of goes along with the accelerated development bullet that you see on this particular slide. The process risk is that it takes away some of the uncertainty, because you may not know, for example, how long is it going to take to develop a particular say user interface, to develop a particular engine to do something, right. So, for example, it may be an ERP system that you are developing, and you need a database design for the ERP system to store a set of data. But if the database schema is already available and can be entirely reused from another ERP like project that was being done before, then you know that amount of time you do not have to budget into your process, and it takes a risk of estimating the software development effort, it brings it down significantly. At the same time, it accelerates development, right. So, that is also a process related benefit that you get out of reuse, because you can proceed much faster. There are things that you do not have to do by hand that are already available. You may have to verify that it indeed does what is it that you want it to do, and that those are some of the conditions, as we shall see, to reusing components. And there can be compliance to standards, because typically when a component is built to be reused in multiple situations, it is built to some kind of a standard, because that is the easiest way of ensuring that it is applicable across a wide variety of situations, across a wide set of systems. And therefore, when you reuse such components, you automatically become compliant with these standards without having to make any additional effort. And what you are essentially really bringing to the fore in the case of reuse is that you are reusing that intellectual property that went into creating the component in the first place. Instead of having to bring the people who built that component and make them build it again, you are basically capturing that intellectual property. You're making effective use of the specialist knowledge that existed. So, it may be a domain specific component that you are reusing. So, for example, something that would build a business process flow, automate a business process flow. This could be a back end server side component that knows how to control workflow. And this can be reused in several, it can be embedded as a workflow engine, and the workflow engine now becomes a component that can be used across any project that requires a workflow. You do not build your own workflow engine anymore. Just like you wouldn't build your own database, you wouldn't even think about building your own database today. You would always buy a database and you would just build your own schema and insert it into the database. And so, just as we have taken infrastructure for granted almost today, the question is, can we raise that level of abstraction and take application components, frameworks, and indeed entire applications for granted, and then build on top of that instead of doing all that all over again. Now, at the same time, while you've seen all the benefits, it certainly comes with certain costs, right. There are some requirements for design with reuse. The first thing is it must be possible and easy to find the appropriate components to reuse. So, there must be some kind of a component repository that has been set up. It must be easy to search that repository. The components must be very well documented, otherwise you may not be able to find the components at all. Even if you do find a likely component, you may never realize whether it fully solves your problem. And there are only two ways of going about doing this. One is you test the component thoroughly to figure out, and you kind of take it apart and figure out whether it meets your needs, or it comes with the appropriate documentation. And when it comes to the documentation, then you do not have to spend as much time in trying to figure out whether it is appropriate for your needs, and that is the real benefit, that you are going to save time at the end of the day. And certainly you need to have the confidence that this component is complete, the component is solid in terms of the capabilities it provides. So, it has been thoroughly tested, and that it will be reliable and it will behave exactly as has been specified. and that confidence can come out of various means. It can be, for example, certified by some kind of a standards body that can say this component has been certified, it has been tested independently other than the persons who developed the component. The other way of gaining confidence is that it has been used in several situations, production situations, to build real systems before you are picking it up and using it in your particular project. So what is the flip side of this? So far we have seen all the things that are great with reuse, and how you can save time, how you can save money, how you can build more reliable systems, and so on. But reuse comes with its own problems. So why do people not adopt it is the question. If it is so great, then why wasn't this something that was that had been adopted, say 20 or 30 years ago? There can be increased costs of maintenance. The one thing that you can point to is that if something goes wrong and now you suddenly end up losing confidence in the components that have been reused, you might have to go figure out whether this component is indeed the one that is responsible for the errors that are being caused. How do I fix this at this point in time, because you will not have access to the source code of these components or the frameworks that you end up using. It's typically a black box kind of reuse that happens. And there may be lack of tool support also. Most IDEs today typically do not support the notion of visually gluing components together as opposed to writing code. Most IDEs or interactive development environments are targeted towards allowing you to write code efficiently, not necessarily targeted towards building systems by gluing together pre-built components today. So the tool support is still not very good. A lot of IDEs today do have some level of reuse support built into them, especially at the level of user interface components. But when you go to the backend server side part of the system, you will not find much available in terms of tool support. The third thing, which may be one of the hardest things to deal with, which is just because it is something that is hard to get your hands around, is something called the not invented here syndrome, or the NIH syndrome. This basically deals with the programmer's attitude that they want to build everything as opposed to using something that somebody else has constructed for them. It stems from several sources, and we will not go into that discussion here. This has kind of been well studied. Several papers have been published in this area as well. Then the costs of maintaining a component library. There's no well-known place that you can go to buy software components, right? Certainly applications are fairly well advertised, but if I had a particular need for a component, there is no universal component repository or a library that I can go search for and find one of these things. So it may be something that you have to maintain at your own site, and the cost of maintaining this kind of a library becomes quite expensive. And the same thing is what the last bullet here is talking about, is finding and adapting reusable components. Now, so adaptation is a different problem than the finding one. So you may find one, but it may not be something that suits your needs exactly, and you may have to adapt that component. You may have to, so in object oriented terms, you may have to redefine some of the interfaces of that component, which means you have to understand how the component is put together internally. That implies that it is no longer black box reuse that you're doing. You're not kind of taking the whole component as it is and just plugging it into your system, but you have to take it apart, understand what it's doing, and then redefine some of the pieces of its functionality so that it becomes appropriate for your use. Same time, you might be deriving some benefit out of the whole thing because the component exists and it has done some work for you already. So let's start taking a look at the different forms of reuse that can exist. Remember, we said that there are different levels of reuse, and this is related to that. The first one is that of generator-based reuse, and these manifest themselves in the form of program generators, code generators, and so on. The second one would be component-based software engineering. We've already mentioned this. So you're reusing components, you're creating and reusing reusable components. So there is the both sides of the equation, design for reuse and design with reuse. Then there are frameworks that we can take a look at, application frameworks, which are basically ways of reusing high level designs of architectures and some level of code. So there are abstract interfaces that are provided that have to be concretely defined in your project. but largely it's possible to reuse a lot of the design complexity that has been solved by somebody else. Then there are what are called application families or product lines, and these also end up reusing a lot of the underlying infrastructure and the core ideas. And finally, we will take a look at a fairly recent phenomenon called design patterns, which basically allow you to reuse designs, and just designs by themselves, not necessarily code or not necessarily entire systems. So what is generator based reuse is the first thing, right? We've heard of the notion of a code generator. A compiler, for example, is composed of a parser, a lexical analyzer, a parser, and a code generator piece. Once it analyzes whatever has been parsed, it is able to generate the appropriate piece of code. Now, if you extend this notion to being domain specific, for example, then we can generate entire programs out of some kind of a specification, right? And this in a way is the reuse of algorithms, the reuse of notions of designs as well, because you can write out, let's say, a specification, and if you take a look at financial systems as a vertical segment, then suppose there is a program generator for financial system which very well understands some of the elements of the workflow, some of the algorithms that are embedded within it. So for example, if an invoice has to be generated in a financial system, a tax has to be imposed on that invoice. So there is an original amount to be billed, and then there is a taxable amount, right? So that notion can be embedded within the program generator itself. It can also, for example, have tax tables that are built into it, that it finds out what the tax is and then just plugs it into this particular program. So the notion of reusing algorithms, patterns that exist in certain vertical domains, and embedding these within the program generator itself leads to what's called generator based reuse. This is possible certainly when there are domain abstractions and their mapping to code can be very clearly defined. And eventually what needs to come out of the program generator is executable code, and when you can map these abstractions that you are feeding into the generator to the executable code pretty cleanly, then you have a way of reusing a lot of stuff that is specific to that particular domain. So there are different types of program generators. Parsers and lexical analyzers are very common ones that you end up seeing. Lex and Yak are the two common examples that you would end up using when building compilers. So you wouldn't build a lexical analyzer or a parser, you would just write a grammar, or you would write a piece of lex input, and what the lexical analyzer now knows is it knows how to recognize all those symbols that you have fed in as input. Same thing with the parser. Once it reads the grammar, it now knows how to parse anything that can be constructed out of the grammar. So the parser is being entirely reused. The notions of building an abstract syntax tree out of the parser, that's an algorithm, and there is algorithmic reuse that is happening at this point in time. Also, there are several cases where code is generated. So if you take a look at distributed object technology, which is a fairly new technology, and Corba is one of the standards that is available in this space. There is something called an interface definition language in Corba. An interface definition language allows you to specify program interfaces in a high level specification language. So for example, my bank account has two functions that are available on it. One is a withdraw function, one is a deposit function, and a third function may be that of a querying function to find out what the available balance is at any given point in time. Now you write out this high level specification without writing the code of what the withdraw is to do, and then it generates the backend code. At least the code frameworks can be generated. So you don't have to, for example, write the specification in C language, in Java language, or anything like that. You write out in this high level English like language, and then it translates it into a framework within a specific programming language, say C or Java, and at that point in time you can just fill in the details of the business logic and not worry about writing the code for the rest of the framework itself. So in that case, for example, the account has to be published so that somebody else can access it, and all those functions are automatically generated by the code generator in this case. It's obviously a very cost effective method of doing things. But program generators are very specialized. They are not generically usable everywhere. So a few things that are fairly generic are things like lexers and parsers, but otherwise if you take a look at code generators and case tools and things like that, they're pretty specialized, and it's not very often used. So the reuse through program generation, the process looks like what is shown in the diagram here. You basically give the description of an application, and the description of an application is fed into a program generator. Program generator has some application domain knowledge that it picks up. So this is the notion of the reuse of algorithms. So a parser, for example, here knows what the notion of an abstract syntax tree is. It knows the algorithm to construct an abstract syntax tree given a particular parsing technique, and so on. So to this you basically give a grammar in this case, in the case of a parser, and then it basically generates a program in this particular case that can parse a particular language. So for example, if you wanted to write a parser for Java, you would write down the Java grammar, you would give it to a program generator, and it would generate a compiler for Java in this particular case. The second form of reuse that we are going to go into is what is called component based software development, or reuse at the component level. This is an approach to software engineering that basically relies on reuse at its core. Component based software engineering is the notion of reusing components and building systems by gluing together these components, and often the level of abstraction has been raised to a point where the components are glued together visually, in fact, as opposed to even writing code, and the visual gluing together of components generates code in the back end, which will put all these components together appropriately. And components are slightly more abstract than objects. It actually, component based software engineering originated from the notion of object oriented design, where individual classes and individual objects could be reused in the case of object oriented programming and design. But what was needed was a slightly higher level of abstraction, where an entire concept could be reused in the form of a component. So an example of a component may be a HTML page which has frames, right? So there are certain parameters that can be fed into this component. I want frames on the left side or the right side. I want this many frames within this particular page, the colors of the different background colors of the frames, and so on and so forth. But the component itself embeds multiple objects within it. It may embed the different frame objects, it may embed certain other notions that can be reused through the parameters that have been supplied to the user. So it's a slightly higher level of abstraction than an individual object, very much like an individual object, except that it may combine multiple objects to perform a single set of functions. It's not a single function typically, it's a single set of functions. So a calculator, for example, could be a component, whereas the different objects within it could be things like a mathematical a representation for data, then there could be different functions on that representation for data, and so on. And all these things have been glued together in the notion of a calculator. There could be a scientific calculator object, there could be an arithmetic calculator object, and these two come together within a calculator component, for example. So the components essentially end up providing a service without regard to where the component is going to end up getting executed. So that is another aspect of a component, is that it is built, and there can be many platforms on which this component will end up executing. So for example, the Windows versus the Linux platform could be an operating system classification. So the component has and can be compiled for either of these two platforms, and when you install the component, it automatically figures out as to what platform this is going to work on and generates the underlying code by itself. And that's what we mean by it provides a service at a level of abstraction that is independent of the platform on which it is going to run. Then the interface, the component typically has two interfaces: the interfaces that it requires for it to run, and the interfaces that it provides for somebody to reuse. And we'll take a look at that in this diagrammatic representation. So the component in this case can be considered, let's say this black box is the component. It has two sets of interfaces. One is the set of required interfaces, as they call it, and one is the set of interfaces that it provides, right. Or provided interfaces. So, if you we can extend this to a particular example, and this example can be that of a, let us say, a printing service component. A printing service component, and in the case of the printing service components, it has a required interface which is that of the printer, right. So, this is a printing service which is a slightly higher level of abstraction, and it requires the printer interface itself, because it has to eventually send documents into the printer, and it is going to provide interfaces which we will put out on the right side in this case, where you can get the queue. I will write it outside here. So, send document to print, one can be cancel print order, and so on. So, here is an example of a printing service component which has a certain set of required interfaces as well as provides a set of interfaces that other people can use in order to accomplish some task. So, the notion is that every time you want to have a service to print documents, you do not need to build your own code to do this. You basically pick up this printing service document and embed it in the place that requires it, and then use the interfaces that have been provided on the right side, the provided interfaces, and then you can just call them appropriately. You of course need to make sure that the required interfaces are also present. So, the analogy is clearly one of building hardware out of using pre-built components such as chips, right. You don't build the chips, you don't build the gates, for example, within your hardware design today. You have chips with pre-built pieces of functionality. For example, you may get a 4-bit adder. For example, you may get a piece of memory that stores say 1024 words of 8 bits each, or a byte each, and you can assemble a larger memory set by taking a bunch of these memory chips and putting it together. You can assemble a computer by putting together memory blocks such as this. Even there is a level of componentization. Typically, you get memory cards which contain, so let us say 4 megabytes of memory or 8 megabytes of memory, and each card in turn is built up of smaller chips that contain maybe a kilobyte of memory each. And the entire memory card can be plugged in an extensible way to create a computer that ranges anywhere from, let us say, 64 megabytes of RAM all the way to a gigabyte of RAM, and you can extend that. And this in turn uses other components such as an arithmetic logic unit, maybe a floating point processing unit, a CPU, and so on and so forth, a disk driver, and so on. So, that is the analogy that you should be thinking of when you are thinking of component based software engineering. Can I do the same thing that I do in hardware, in building hardware, to building software systems as well? And that is what component based software engineering is all about. So, components can provide different levels of abstractions as we have noted down in this slide. Typically, most of them tend to be data abstractions or functional abstractions. So, the component either implements a single function such as mathematical libraries that are available. So, there can be libraries of mathematical functions, there can be libraries of UI components, there can be libraries of communication components, and so on, or there can be data abstractions. So, things like data structures, so lists and stacks and sets and bags and hash tables and so on. So, these are data abstractions. So, that can exist as well. Rarely is the component a complete system abstraction, that becomes Scott's type of reuse, but for the sake of completeness we have included all the type of component abstractions that can exist on this slide. The process is something that we will go into next. It can just be fitted into the existing software engineering process, in the sense that you have a requirements phase, and once the specification is done, you typically have a design phase. Now, here is where reuse really comes into the picture, right. You can either reuse it at the specification phase, but more often than not reuse starts in the design phase and is most heavy during the implementation phases. So, given that, what typically happens is you can say that you will extend the normal software engineering life cycle to essentially have a reuse activity within the process. By this, what we mean is that you have a design phase, but as part of the design phase you first go look for components, and if components are available, then you just reuse them and then you design the rest of the system and go on. The same thing for implementation. However, one should realize that this may not work very optimally, right. So, for example, you might go find a component whose specifications do not exactly match the design requirements that you have, whose specifications do not exactly match the implementation needs that you may have. So, it may be a little bit more than what is required, or it may be a little bit less than what is required. In this case, you have an option at this point. One is to put a feedback loop within the software engineering process and change the specification of the system, not change the requirements exactly, but change the specification of the system to meet what the components, the set of components that are available are giving you. So, that is one way of going about doing it. Something that is very important is obviously the prototyping effort in this case, because you are getting many unknown, what are essentially unknown quantities from different places and trying to put them together. You should first have a prototyping phase, or the prototyping phase becomes very important here, where you are trying to first glue them together, possibly using a scripting language, quickly put them together, in other words, just to see whether there are incompatibilities that may exist within the different components, etc., and the components really perform according to specifications and so on. Now, once that is done and you are kind of satisfied, then you can kind of throw the prototype away and rebuild the system with the same components, but now your glue is much stronger. Your glue is maybe a real programming language that has typing support and so on and so forth. So, an opportunistic reuse process, like the first thing that we showed by simply extending the software engineering process, would be to design the system architecture to specify all the components that would be required. So, the architecture itself is specified in the form of a set of components that are required, and now for every component that is required, you go out and search for components that may be reusable somewhere, and if they are reusable, you simply incorporate all the discovered components, and then this entire flow can then be incorporated by saying the rest of the components might just now have to be built, and that is the regular software engineering process at this point. However, the development with reuse, remember what we said, that the components that you may end up finding may not exactly be a match for what is it that you are looking for. So, once you outline the system specification, you should really read requirements as specifications in this particular case. Once you outline the system specification, you search for the reusable components, and depending on what you find, you may end up modifying the system specification according to what has been discovered. And in this case, so for example, suppose you are looking for a list component, your system specification says you need a list, a singly linked list in this case, and what you really find is only a doubly linked list is available as a reusable component. So, you basically modify the specification of the system at this point to say I am going to use a doubly linked list because it really provides all the functionality that would be required, and in this case is an example of the components requirements are a superset of what is really needed within the design that you have created. There can be situations where it is a subset and the component may now have to be extended a little bit as well. And then you do the architectural design at that point in time using the set of components that have been discovered. And now you search for other reusable components and so on, and then you specify all the system components based on the reusable components. So, this is the development with reuse scenario at this point in time, and the last half of this process, right, is not the search for reusable components here is different than the search for reusable components here. Why? Basically because this is the first part is referring to design with reuse, and the second part is referring to design for reuse. So, one of the components that you may be building might look very similar to a generic component that can be created out of this. right. So, what you should do is to then extend the effort to make this piece slightly generic if the project can absorb the cost, because there is a certain cost to be paid when you try to make something more generic, and then you specify the system components that are based on reusable components at that point in time. So, some of the problems that component based software engineering face today are that there can be component incompatibilities, right. So, you may get two components from two different sources, and there may be a standards incompatibility that may exist, even though they both provide the kind of functionality that you need. One may be talking a slightly different protocol than the other one, and the glue that you may have to write now to bring these things together may prove quite expensive. It may be in fact in some cases more expensive than writing the original piece of software from scratch. So, that is one thing that has to be taken into account. The other thing is the old problem of reuse that we already saw, which is finding and understanding these components. So, is there a standard means of describing a component? There is no standard that exists today, for example, for describing what a component does. Even though there are designs de facto standards such as UML that is available, there is no component based software engineering standard for saying here is a description of a component that can be processed by a machine, for example, while doing a search. The third thing is managing evolution of systems, right. If your system is largely built out of pre-existing components and now the system specifications change, the system requirements change, the specifications change, now you may end up in a bind because the existing components may not fit the new requirements that you have, the slightly extended requirements that you have, and if no component is now available to match those needs, you have to write that piece of code from scratch, write that part of the system from scratch, and that can prove quite expensive. So, in some cases you would find out that evolution of the system to support a slightly incremental requirement is much more expensive than the original system that was built, and that does not look very very good. So, what again, so those are the advantages and the disadvantages of component based software engineering, fairly well known methodology that is being adopted today increasingly. A lot of the IDEs end up supporting that if you are using them on any kind of operating platform. So, the next level of reuse that we would like to take a look at is application frameworks. What is an application framework? Is the first thing that you have to ask yourself. And an application framework is essentially a half implemented design, to put it informally. So, what it provides is it is a subsystem design, and it is made up of a collection of concrete components that it embeds and some abstract components which have to be implemented when you use the framework, right. An example of such a framework is the Interviews graphical user interface framework that is available from Stanford University. Here is where they provide a collection not just of individual components by themselves that can be reused, but there is an interwiring between the components as well. So, for example, it might provide the MVC pattern that has been partially implemented. It might provide other design patterns that have been partially implemented, and there is some specialization, there is some configuration that would have to be done if this framework were to be really useful. So, you can't just use the framework as is. If you use the framework as is, it becomes a common off the shelf system that you are reusing at that point in time. So, what distinguishes a framework from a complete system is the fact that one certain abstract classes might have to be instantiated. So, you actually have to write some code that provides some concrete functionality for some abstract classes within the system. The second thing is it would have to be configured according to the system that were being used. A good example of this on the business side would be, let us say there is a inventory management framework. What this means is that it is not an inventory management system. I just can't take it and instantiate it and start using it to manage my inventory. I need to describe to it, the first thing that I need to describe to it is the platform on which it is going to run. The second thing is every inventory management system embeds within it business process of how inventory is managed within the system. So, for example, the business process may be that of an item comes in, it has to be approved by somebody, then it has to be entered into the inventory system at that point in time, and then it is tracked as to the movement of the particular item from warehouse to a particular store and so on and so forth. So, that is a business process, that is a control flow. and unless that flow is described to this framework, the framework is useless. The framework cannot be used as is. And when the flow is described to the framework, what the framework does is it instantiates that particular flow. It makes it concrete, it makes it usable, and at that point the framework becomes a system that can be used directly. So they are fairly large entities. The level of granularity in a framework is quite high. So it might act as an entire system. For example, it could be a framework of an inventory management system or an ERP system within the industry, or it can be a framework for GUI designs such as MVC designs and so on. So it's fairly large. However, there has to be some work that is done by the person that is reusing the framework. So there are different classes of frameworks that are available. There are system infrastructure frameworks, there are middleware frameworks, there are application frameworks and so on, depending on the level in the stack that you are at. System infrastructure frameworks basically are things like communication framework. So there may be a socket based communication framework, there can be a multicast framework that is available that supports multicast based on IP or something else, things like that. So there can be user interfaces frameworks and so on. Now the middleware integration frameworks are typically those that support a certain standard, such as Corba, for example. It may support a J2EE standard, it may support a .NET standard, and they support communication between components here. The framework, for example, may go beyond simply a piece of middleware such as an ORB by saying I am going to provide reliability to this piece of middleware by replicating the object in multiple places. So it's a framework for object replication, in other words. So that's the notion of middleware at the that's the notion of frameworks at the middleware level. And finally, frameworks at the application level are those that develop that support the development of specific applications. So inventory management was an application that we just talked about. There can be frameworks that do different types of vertical domains as well. So a framework that does account management, for example. So some things that have to be fed into that would be the account management business process, the tax tables for the account management. So it needs a lot of things, just like a component has certain required interfaces and it has certain interfaces that it ends up providing. A framework also has certain requirements, the things that it ends up depending on, as well as it has a set of services that it ends up providing. So frameworks are meant to be slightly generic because they can be instantiated in different conditions and different circumstances with different requirements. So the framework can provide an entire family of applications, if you will, each one characterized by its own configuration, by its own business process, by its own business rules and so on. That's another example of the variability of a framework. For an application level framework, there could be a set of business rules that are different within every company. So for example, the discount rules that are to be given when doing invoicing. One company may say that we don't give any discount at all, that's the rule. The second company that ends up instantiating the framework may give a business rule stating that if the invoice is over 100,000 rupees, then a discount of 5% is going to be applied to this. A third company may say that any customer who has had business with us over the past 3 years to the tune of say 10 million rupees is going to get a 10% discount on any further purchases. So there can be different business rules that have to be provided to instantiate the framework as well. Typically extending the framework would imply that you either do some development, in which case you are adding certain concrete classes to the framework that actually implement some functionality that are provided as abstract interfaces within the system, or you add certain methods that are called in response to events that are recognized by the framework. So these are called callback methods, and every time the framework recognizes a certain event. So suppose your total business volume has crossed a certain threshold. Now it's impossible for a framework writer to figure out what you want to do when you cross that threshold. Maybe you want to set up an alert, you want to send an email to a bunch of people saying the business volume has crossed the threshold, maybe you want to set up a press release, etc., etc. Now the framework writer who is writing a generic framework has no idea. So what he does is he says that I am going to generate an event of type business volume threshold exceeded, and when this event occurs, then I am going to call one of these functions which is described in an abstract way. So, there is no implementation for the function, he has just called one of those functions, and it is up to you as the framework instantiator to implement that particular function. So, you have to write the code to receive that event and appropriately act on that event. Another example could be that your average execution time for a particular servlet that was executing in the web tier is suddenly spiked up by 50%. And the framework, an application management framework may give you that event and say it's up to you to do what you want with it. You can raise an alarm, you can try to take auto corrective action, and so on and so forth. The typical problems that exist with frameworks is the complexity, right. So, the framework is not like a single component which can be easily understood. The printing service component was fairly simple in nature. It had a small set of interfaces, typically 2 to 3 interfaces are what make up a component. It may contain like 4 or 5 objects that build up that particular component. So, it is not very large in size and is easily understood, and is also easy to discard and replace. That is the other advantage of a component, is that if you find that the evolution of the system does not support that component, then you can replace it with another one fairly easily. But a framework is a much larger commitment because of the size. It is almost an entire subsystem all the way to being an entire system by itself, right. Once it is instantiated, it could form the bulk of your system. In such cases, it is obviously not easy to replace a framework, therefore, evolution of the system may become much harder. Also, understanding the complexity that goes into creating one of these frameworks and therefore specializing it to meet your needs, to configuring the framework, for building these concrete classes that have to be added to the framework, for dealing with events that the framework may end up throwing up, are all very difficult to do in certain cases. Obviously, it has its own advantages. It is saving you a lot of development time, a lot of development effort. This has been again well tested. So, it is a level of reuse that is much higher than that of components, but it also comes with a certain baggage that you would have to deal with. So, going forward, what we are going to take a look at is the remaining levels of reuse families. We are going to take a look at design patterns and levels of design reuse, and how what are the benefits and the disadvantages of doing reuse at those levels.